I've already mentioned that the energy contained in a wave is a square of the wave height, right? So in a fully developed sea, you also need a scale for the kind of energy that's coming in with the waves. So in a fully developed sea at equilibrium, which means the storm, remember we defined the sea and the storm. The storm has been there long enough, or it's moving fast enough that it has reached some equilibrium condition with the ocean, so it cannot put in any more energy into the ocean, so the waves cannot grow more. No more energy cannot go into the ocean. And we said the swells get sorted out and they outrun the storm because they have a long wavelength and their wave celerity is greater than the speed at which the storm is moving, or maybe the storm is not moving at all. So the swell is essentially these uniform symmetrical waveforms that travel out from the storm area. They have nice long crests and they transport energy to very long distances, as I measured before. So looking at this table again, we said it's the wind speed, wind fetch, the length over which winds are blowing, and the duration over which these are blowing that determine the energy of the waves coming in. I also mentioned it in the context of the surf coming in at the west coast of the US versus the east coast. For example, we said Pacific is a much bigger ocean and the winds are westerly, so there is a long fetch over which the westerly winds are putting energy into the ocean. So we will see later on that the west coast of the US is also very different than the east coast in terms of the choppiness, the slopes, the rocky nature, and so on. So much more surf is created in the west coast for surfers. They love it because the topography and the wave energy combine to form a lot of breaking waves and various forms of breaking waves which are favorable for surfing. East coast has westerly winds coming off of land, so generally soft waves at the coast. So you can look at the wind speeds in kilometer per hour going from 20, 30, 40 and so on to 90. You can look at the fetch in kilometers going from 24 to more than 2,000, almost 2,500, and the duration in hours going from about 3 hours to several 2.5 3 days almost. Okay, so obviously all these combinations matter, and you can see that average height depends on these combinations, and you can get wave height of almost 14 meters here at 90 kilometer per hour winds over 2,446 kilometer fetch, blowing over 65 hours. So average wave length here in meters will be more than 200 feet. So the average speed in seconds is average period in seconds is almost 14, and the height of the 10% of the highest waves is 28.4 meters. Okay, so obviously it decreases as the wind speed decreases, the fetch decreases, and the duration decreases. Okay, so that's intuitively obvious, but the table makes it clearer. Swells are these long wavelength waves, so they travel faster and they outdistance the other shorter, slower waves. They form nice wave trains, so they are groups of waves that are traveling together. So constantly waves are generating by the storm in the sea, and waves are constantly emanating. Swell is constantly outpacing and forming these groups of waves or wave trains, and waves disperse, so they basically means different wavelengths get sorted out, and the longer wavelengths, faster waves move ahead, and there is a decayed distance associated with the waveforms. It's basically the distance over which waves change from the choppy sea near the where the storm is to this nicely sorted out swell, which is like a bobbing nice ducky that we saw. Okay, so wave train speed is half the speed of an individual wave. What does it mean? You can probably do this experiment. If you throw a little a stone in the pond, and you can see that there is the waveform, and it seems like there is a wave train moving at a different speed than the individual wave. How does it work? This tries to explain it. If you don't understand it, don't worry about it, but if you want to learn more, you can go and find more animations and so on. But remembering that this is an idealized situation where there are not a lot of other factors like winds blowing away the waveforms and so on. You have a wave train with let's say 4 waves that are starting out here. There is a storm here, let's say, which has produced these waves, and these have already been sorted out into swell. As the wave train moves forward, the front of the wave train dissipates its energy, gives away its energy to the ocean, and behind the wave train, a new swell joins it. Okay, so the wave train has moved from there to there. The front of the wave train has died out, but the back of the wave train has achieved a new or received a new wave form in the wave train, and then the second wave dies out, and so on. So this wave train is moving at a certain speed, and each wave within it is moving at a certain speed, which is what this is saying, that the wave train as a whole is moving at half the speed of each of the wave. Okay, so you can think of it as a group velocity versus wave speed. This determines the speed of the energy transport and so on and so forth, which we won't get into, but if it intuitively makes sense, you can try to remember it. Otherwise, you can either learn more by looking at more animations. The equations are kind of complicated. I won't go into it in this course, but you can definitely learn more about it. Watching an animation will actually make it much clearer. You can clearly see the wave train and individual waves within the wave train. Okay, it's cute, so look it up. Good. Let me stop this then.